My name is Andreas Weis. I work for Woven by Toyota as a vehicle architect, which means I write safety-critical software for vehicles. I'm also one of the co-organizers for the Munich C++ user group, which is one of the largest C++ user groups in the world at the moment. We're always looking for speakers, so if you want to give a talk, if you want to practice a conference talk, even if you're not an experienced speaker, please reach out. We're always happy to welcome new faces. So many of you are probably familiar with the title of this talk, in case you haven't seen it before. It comes from this book, 97 Things Every Programmer Should Know. It's a pretty good book if you haven't looked into it. It is like little bits and pieces of advice from like different software engineers, like sharing their knowledge. And my favorite piece of advice from this book is the item number 55 from Scott Myers, which says, make interfaces easy to use correctly and hard to use incorrectly, simply as a design guideline for how we should write our interfaces. So this guideline really has two separate pieces of advice. The first one is the easy to use correctly part. And I'm just going to quote from the book here what is meant by this. So it says, people using a well-designed interface almost always use the interface correctly because that's the path of least resistance. In a GUI, they almost always click on the right icon, button, or menu entry because it's the obvious and easy thing to do. In an API, they almost always pass the correct parameters with the correct values because that's what's most natural. With interfaces that are easy to use correctly, things just work. This has also been propagated by other people under different names, like there was this great talk by Kate Gregory a couple of years back at ACCU, where she was giving the same design guideline and calling it the pit of success. So the image here is like if you're stumbling in the dark, you don't really know where you're going, and then like the first pit that you fall into, that should be the pit of success. So this is really the same idea. This term pit of success is pretty popular inside Microsoft, and it was brought like to a wider audience by a blog post by Brad Abrams in 2003. And then there was again another blog post by Jeff Atwood in 2007, which became pretty popular. So that's probably where most people have heard of it. So this covers the first part of Scott Myers' guideline, which is like how to make the interfaces easy to use correctly. And I'm not going to talk about that first part here. So if you're interested in that, please check out Kate's talk or some of the blog posts. But this talk is actually about the second part, the hard to use incorrectly part. So again, to quote from the book, Scott Myers says, good interfaces anticipate mistakes people might make and make them difficult, ideally impossible to commit. A GUI might disable or remove commands that make no sense in the current context, for example, or an API might eliminate argument ordering problems by allowing parameters to be passed in any order. So today we're going to talk about how we can build interfaces that are hard to use incorrectly in C++, and our primary tool for doing that is going to be the type system. We'll start out by doing a really brief recap of like the common categories of precondition violations, so like things that can lead to incorrect use of an interface. Then we will take a look at how we can leverage the type system to prevent precondition violations. And in particular, we will focus on two areas. We will look at different techniques for restricting access to data and techniques for restricting control flow. So before we start looking at some code, I want to point out that all of the code here is slide code. Lots of the examples are incomplete and probably not something that you will find in production code. It's always meant to illustrate a specific point and get something across. So please don't be thrown off if they seem overly simplistic or naive in places. So yeah, let's talk about precondition violation and start with a really obvious example. So here we have a vector. We set it to 10 elements, and then we access out of bounds. So the array access here, that's an obvious precondition violation, right? It's a precondition of the subscript operator that the index that we give it to must actually point to a valid element of the vector. So this is pretty clear. This is an incorrect use, and it's a violation of the function's contract. So to briefly recap, the contact of a function is usually stated in terms of preconditions and postconditions. And what the contract promises is when I call the function within the preconditions, then the contract guarantees that the stated postconditions will be established by the execution of the function. And when calling the function outside of those preconditions, the contract doesn't guarantee anything, right? So this is basically the same behavior as you would get with undefined behavior in the language. Right? We just don't say what happens. Very weird stuff might happen. Please don't make any assumptions. So the violation of a precondition is always an incorrect use. And when we're designing our interfaces and we're choosing our preconditions and we're deciding how the function can be called, this is what we want to avoid, right? And there's several approaches how we could go about this. The first one is, again, staying with the example for the vector, we could just widen the contract, right? We could just remove the precondition and say, well, if you give it an invalid index, there's still a defined result for this. In the case of the add function, it will just throw an exception. So what happened here is we now established a new return channel for the error. This was necessary because in the context of this function, if I give a bogus index, there's really no sensible thing to return anymore, right? So like establishing a sensible precondition in this case is really hard. So what we had to do here is we had to establish a new return channel that gives us back the error. And that already shows you that we just complicated the interface quite a lot by doing this. The error return now becomes part of the function contract, so that the user can rely on this occurring. But they must also be prepared to handle this, right? So if the user is not sure that they call the function within the preconditions, then they need to be prepared to handle the error. So the exceptions here try to hide the fact that the contract is widened, right? Like the function signature did not change, and like we just have this new return path for the exception. But this is not always desirable. So let's look at a different approach that we could take here. If we look at the square root function from the math library, obviously taking the negative square root of a number, if we're talking about real square roots, is not a sensible operation. So what we do here is this function will return a nan, a float nan, right? So we extend the range of possible values of the return type, and then we just reserve one value of the return type for the error case. And yeah, in the case of floating point, you've probably seen this. This nan value then is kind of infectious. It propagates through following subsequent calculations. So it's hard to ignore, and it has these special properties. But again, the fact that we violated the preconditions, the interface tries to hide that away from us, right? So we won't see this probably when we call the square root function, but it will probably surface at some later point. So widening a contract reduces the number of preconditions, but what I would claim what it does not do is reduce the opportunities for incorrect use. Seemingly that seems to be the case, but the problem is if I widen the contract, my postconditions also become more complex. And that again introduces new opportunities for incorrect use in other places. So in a way, I just shifted the problem down the line. What's worse, many preconditions are simply not detectable, so widening the contract is kind of hard to cover this. So my assumptions going forward would be that widening contracts, in some cases, it might be a good solution, but it's not a good solution in the general case. It brings problems of its own, and it would actually be nicer if we could actually prevent the incorrect use instead of trying to hide it away under a wider contract. So again, stepping back, what actually is an incorrect use? Like a typical example, you probably all made these mistakes. I for sure have made these mistakes several times. I want a function that takes in a buffer, and before I do any computation, I just want to zero out the buffer. I'm using memset here, and of course, my mistake was that I switched the arguments, right? The size goes in the third place, and the zero, the value that I want to set the buffer to, goes in the second place. So this is even trickier than what we saw before, right? Like here, I am calling the function within its contract, right? This is perfectly valid. I'm just setting 0 elements to whatever the value of the size is. But this is still an incorrect use, right? This is still not what I wanted. And ideally, I would like to address it that people could accidentally make this mistake. And fundamentally, really what is happening here is a units error, right? Like we have the size is a different kind of quantity than the value of the elements. So that's what makes this possible. And if we look at all the categories of errors that we saw in the examples so far, they're really all kind of domain errors, right? It's all I was passing an invalid argument to a function, and that's what violated the preconditions here. So that is one of the major categories of interface misuse that I want to protect against. Is I want to make it harder for people to accidentally pass invalid arguments to functions. So let's look at some more examples that actually don't fall under this umbrella of the invalid argument errors. So in this example here, I want to just read some data from a file stream. And my mistake here was I did not open the file stream. It does not actually point to any file, right? I just default constructed it, and then I tried to read. And yeah, this code has several issues. So first of all, the read function here does have a wide contract. And again, the way that this is realized is that there is an additional error channel. In the case of a file stream, there is an error state inside the stream object, which I was supposed to check, which I didn't do here. So I don't see the mistake. So the stream here clearly is in the wrong state to carry out the read. So the question here is should I be able to read from a closed stream? Should this operation be allowed? Is that a sensible contract to just say, yeah, you can call read? And if not, then how can I avoid this, right? How can I enforce a constraint like you must only call read if you actually opened the file before? A different example is if you have a mutex, you have these lock and unlock functions, and there's constraints on the order in which you can call them, right? If you just call the lock function twice in a row without unlocking in between, you have a deadlock, right? So this is also a misuse of the interface. And what I would like to enforce here is like, you must not call lock twice in a row without calling unlock in between, right? So again, a different kind of violation than we had in the example before, but again, not a violation that is due to an invalid argument. And then this example here, I think, is particularly tricky. So what we do here is we have a vector, then we obtain an iterator to the vector, but then we call a pushback on the vector, which invalidates the iterator, right? The pushback might resize the buffer beyond the capacity, so we need to reallocate, and then the iterator is basically like a dangling pointer. So if I try to dereference it after the pushback, this may or may not work. And this is a particularly nasty example, because what happens here is we have this kind of spooky action at a distance, right? If you see the lines right next to each other, like here, it's pretty obvious. But if you imagine I take the iterator, then I just store it away in some place, and then a lot of stuff happens that also happens to invalidate the iterator, and then at a much later point, I take the iterator again. This is super hard to debug and super frustrating. So the problem here is, of course, shared mutable state. Sean has talked about this a lot, also in the talk that he has given earlier this week. It's a well-known problem. Other programming languages go to great length, actually, to make this very difficult. The last example that I have, this is a thing with C++ move semantics. If I move from an object and then I try to use it again afterwards, this usually does not work unless the object gives special guarantees that enable this, which in most cases is not sensible. Such a use after move is a misuse. So this could be easily prevented actually by the language rules. Other languages have different ideas of move semantics. Maybe it should be prevented by C++ as well. We will see some examples later on where it would be really useful if the language actually did not allow this use after move. Fortunately, Clang Tidy has a checker that allows you to enforce this behavior. If you use the bug-prone use after move check, then Clang Tidy will actually warn about something like this. So the tool there will assume that the move always destroys the object, and then unless you reset it to a valid state by assigning to it, you cannot do anything with it anymore. You can't just call arbitrary member functions. So all of these examples, I would summarize under the term of invalid context, right? You're calling a function, but the context in which you're calling the function is just wrong. So if we look at the two categories again, like the invalid argument, that's like you pass a negative number to the square root, you pass a wrong index to an array index operation, you pass a null pointer or an invalid reference to a function. And the invalid context, that is, for example, you forgot to call the init function on a type that requires two-phase initialization, or you're accessing an invalidated iterator, right? The iterator is in the wrong state, it's in the wrong context. Or you read from a file handle after it was closed or before it was opened. And the question for this talk is really, how can we prevent these kinds of violations? And I said it already in the beginning, the type system is going to be our tool of choice here. And if you take a step back and think about like what does the type system actually do? What is the role that it fulfills in the language? Then we see that it allows us to do two things. It allows us to restrict the set of values that are assigned to an object. And it allows us to restrict the set of operations that can be carried out on an object, or determine the set of operations. And these two are actually pretty good matches to the two kinds of precondition violations that we saw earlier, right? So this seems to be like a good tool to address this. And we will now look at several examples and several techniques how we can make use of this and try to capture some common misuses. So we'll again start with the invalid argument problems, because those are usually easier to grasp. The first example that I brought here is this function from OpenGL. If somebody did some OpenGL programming, they probably remember this. This GL text image 2D, that's the function that you use to specify a texture for 3D rendering. So a texture is basically like an image which has like all kinds of properties that describe the size of the image, the format, and certain properties of it that are relevant for interpreting its contents during rendering. And the problem with this function, and if you've used OpenGL, you probably have done these mistakes, is that this is a valid way to call this function. So nothing here is typed, right? All of the arguments are basically just ints or convertible from int. So yeah, it's really easy to mess this up, and it's really easy to write code where you just cannot see what is going on, what each parameter means, whether the arguments are correct or not. So the GL enum type here was just a type def for an unsigned int. What is worse, all of the enumerator values that you can use, for example, for specifying a format, are all defined as preprocessor constants in OpenGL. Some of those values even overlap, so you might accidentally get it correctly because just two unrelated enumerators happen to map to the same integer values, but this is then like non-portable, right? It could work fine on Windows, and then you try to compile it on Mac or Linux, and it just breaks, and you have no idea what went wrong. And again, if you just look at the source code, it's really not obvious. Like you see, yeah, well, there's like a format here and a border and everything, but yeah, you just switched the order around. So super annoying. The compiler basically will never catch anything here. In the best case, you will get a runtime error. In the worst case, the call will just pass, and then your rendered result will just be wrong. So that's now an interface that is really easy to use incorrectly. And the obvious solution is just use stronger types, right? Don't make everything be an integer. So particular like with the GL enum and the enumerators being defined through the preprocessor, there's a very easy fix for this, right? We can just use the enum classes for C++, where we can define all of our enumerators, and then if we try to mess it up, if we give the arguments in the wrong order, if we try to assign a color to a shape, that doesn't work. If we try to assign just a number to a shape, then we at least have to opt into that with a cast, which should be a clear indicator to a reviewer that this might be a problematic place. So enum classes have a nice property in that we can use them to build a very simple version of an opaque type def. So let's, for example, say I have a function that creates some kind of resource, and it gives me back a numeric handle to that resource. So instead of just having the handle be a type def to an int, I can use an enum class like this. And then, yeah, I can assign to that valid handles. I can assign to that like this special invalid handle value to initialize it. I can still assign numbers to it if I use the brace initialization, but at least I cannot assign numbers to it with the this kind of initialization. And if I have different handle types, then they're also incompatible. So this is not a perfect solution, but it's a start, right? It's better than what we started with, where everything was just an integer and everything converted to everything else. I can go one step further by having a proper opaque type. So what I do here is I actually build a struct, which then holds the numeric value as a member. Since I don't want to write out 100, I will probably have more than one handle type, right? And I don't want to keep repeating the same code for each of these handles. I just put it in a template. And then I can just use like unique empty types to tag these different handles, so that I end up with these different handle types in the end that are not convertible to each other. So in this case here, if I have a file handle and a process handle, then I cannot assign a file handle to a process handle or vice versa. So this is a much stronger protection than the simple enum-based type defs. The disadvantage here is that they don't come with batteries included. So if I want to have comparison, if I want to store them in a map where I need the less than comparison, if I need a hash function, if I want to print them to the console, maybe like not for handles, but like for unit types, I might also want to do arithmetic, right? So all of this on integers, I have this available. If I wrap the integer in such a struct, then I have to write some code to make this work. But you can provide this in a way that providing these operations again becomes easier. So in particular, there are libraries already out there that provide a lot of infrastructure to do this. Like Björn has this strong type library, which is really nice. Or if you want to wrap numbers for units, then Matoush has this his units library. Both of them are here at the conference, so I'm sure they will be happy to give you an introduction to those libraries. So let's go back to our memset example that we had in the beginning, where it was easy to confuse the arguments. So one way to address this is to use an interface like we see here below, right? So by using a span instead of like 2 arguments for the buffer and the size, it becomes much harder to confuse the size with the fill character, right? Because here it's, I mean, you see it on the last line where you have to call it, you have to construct the span, and it would be pretty obvious if you confuse the size and the value here, at least much more obvious than it was before. So structuring the arguments properly instead of just having like a long list, like this long list of inst, like we saw in the OpenGL function, can also help a lot with making it harder to use incorrectly. So what about this version, right? This is also something that people sometimes do, like especially when they have functions with a lot of arguments, then instead of having this long argument list, they just have a single struct that contains all of the arguments as fields. I used to not like this very much because it was kind of cumbersome to use, but C++20 introduced an interesting feature, which is the designated initializers, which allows you to like actually name the fields when you initialize the struct with the curly braces. And I really like this. Like, this is probably my favorite feature of C++20. And if you have this available, then I think this kind of interface is a lot more viable than it used to be. Like, the code is really expressive. I mean, you cannot force the user to use the designated initializer, right? They could still write the just the comma-separated numbers, but it allows you to write pretty expressive code. And if you sometimes you're forced to deal with APIs that accept structs as arguments, and then I find that the code just becomes a lot more expressive if you do it this way. So one typical example where I think the benefits of this become obvious is like if you want to construct a rectangle, right? And you give it 4 numbers, but it's actually not clear what the 4 numbers mean, right? There's 2 possible interpretations here. It could be 2 sets of coordinates for the 2 points at the corners of the rectangle, or it could be 1 point plus the extents of the rectangle, right? And if you just give 4 numbers, then if you just read the code, you don't know, right? You actually have to open up the documentation for the class to see it. If you use structured arguments, then it's a lot more clear what it means. And if you get it wrong, it's a lot easier to spot. Besides having a structured argument, another very powerful tool is to enforce structured data access. So many of you have probably used variant before. And usually when people see variant for the first time, the way that they try to use it is like this. So I check which type is actually the active type of the variant right now, and then I branch based on this, right? And then I have like several branches for each of the different shapes. And this is straightforward, this is very intuitive, but it's also very brittle, right? I could just forget to handle one of the cases, right? Maybe I got distracted in between, and then whoops, just one of the shapes slipped through. What is worse is if this variant changes at any point in the future and somebody adds a new shape, then I need to manually review every single one of those branches in my code base, and the compiler is not going to help me to find the ones that I did forget. So the more sensible API here for using the variant is the visitation, because with the visit, if I forget to handle one of the alternative types of the variant, it will be a compile error, right? So there's a whole class of mistakes that I could make with the if that just disappears here. And then in particular, if you use this little trick here at the top that allows you to create an overload set from a variadic pack of lambdas, then you can write pretty compact code with that as well. So in case you haven't seen the trick before, the idea here is really, you can think of a lambda as just a class with a function call operator. And what we're doing here is we're inheriting from all of these lambda classes, and we're pulling all of their function call operators into the namespace of this enclosing overloaded struct. So then when I do a name lookup on a function call on this overloaded type, then it is able to get to any of the lambdas by that. That's a pretty neat trick, and I like to use this a lot with visit. It's very useful. So let's take this into a slightly different direction and look at how we can limit access to data in the case of friendship. So friendship is not everybody warns about friendship, right? Like if you look at the coding guidelines, if you look at best practices, then there's usually they usually restrict the use of friend or just like try to forbid it outright. And the reason for that is it's a very coarse tool. So if we imagine you have a database class like here, which has a retrieve data function, and then it has another retrieve function that gives access to privileged data. And all of the clients are able to retrieve data, but the privileged data, like only certain clients that are privileged should be able to call this function. So you could give the privileged client friendship to allow it to call this function, but friendship will also give it access to the internals, to the private state at the top. And that's not what you want, right? That's what makes friendship dangerous. So the question is there a good way to just give access to the retrieve privileged data function, but not to the rest of the internals of the database class? And one way to do this is the passkey idiom. Arne actually wrote a nice blog post about this. The idea here is simply to create a type that represents the right to be able to call this function. And now the friendship that we give to the privileged client is the friendship to this access token type, right? So the access token has a private constructor. So normal code cannot construct an access token. They cannot obtain it because they cannot call the constructor. Only the privileged client can, because they have the friendship to the access token. And now, in order to call the retrieved privileged data function, I need to present an access token. So this is not a full encapsulation, right? I mean, the client, like if you type in your IDE and you type like .retrieve data, then in the autocompletion it will still show you the privileged data function, but you cannot call it accidentally, right? Because you won't be able to produce the access token. So that allows you to give this very fine-grained kind of access and friendship here. The last thing that I want to look at in this class of preventing invalid argument errors is declarative interfaces. So again, I have an example here from OpenGL. So if you have done modern graphics programming, modern GPU programming, you probably know that you have two kinds of programs, right? You have one program that runs on the CPU, and then you have a different program that runs on the GPU. And now all that the CPU code does is it sets up all of this data in the memory of the GPU, and then eventually it hands off the control flow to the GPU, and it says, this is where I stored the data, this is what the data looks like, and this is the program that I want you to run now. And one of the more error-prone things here is that if you mess up the description of the data layout, then you can get some really funny bugs. So for example, a common thing that you have to do in OpenGL is you have to describe what your geometry data looks like in memory, right? So here we have a layout where we have like different coordinates for the position of points in space, the associated normals for each of those vertices, and the texture coordinates for each point, right? And it's laid out in a specific way in memory. And now what I do is I call these OpenGL API calls where I describe this data layout. So I have to give like all different kinds of offsets and describe where it can find all these different coordinates. And this is very easy to get wrong. It's easy to make errors there, and you won't find them until you run the program, and then it's going to be fun to debug. What you could do instead here is switch to a more declarative interface. So you need to load the geometry data into memory anyway at one point, right? So you probably already have a struct on the C++ side of your code that contains the data structure for a single vertex, right? And that tells you, like, there's a position, there's a normal, there's a texture coordinate, and these are the sizes. So what you could do now is, instead of just like writing this struct and then figuring out the numbers that you pass to the API, you could use a more declarative API that then allows you to programmatically extract this information, like the offsets and the sizes, and then wrap this, the calls to the OpenGL API behind an interface that reuses this information from the declarative API. So I only sketched this very roughly here. There's actually quite a bit of machinery that you need behind the scenes to make this work. You need to do some meta-programming because we don't have reflection, which you would normally use for something like this, but it can be done, right? And once it's written, then actually doing the API calls for specifying the data becomes a lot easier and a lot less error-prone. So with the declarative interface, the goal is always to specify the what instead of the how. You want to restrict what can be expressed to the set of sensible values for the kind of problem that you're trying to model, and leave just enough customization, just enough space for customization for what is reasonable within this domain. You can deduce quite some tricky configurations from such a thing, since like you can put in an arbitrary amount of machinery behind this, right? So you can get really clever here. One caveat is that usually by abstracting in this way, you lose some amount of expressive power. So when doing something like this, you probably want to leave an escape hatch instead, that people want to do something that you did not consider in your abstraction, and you don't want to prevent them from doing that, right? You just want to make it harder to accidentally misuse the underlying API, but you usually don't want to encapsulate it away completely and like forbid access to it. That would usually be too restrictive here. So all of this were techniques now that address the first kind of violations, the invalid arguments. For the second type, the invalid context, we need to switch gears a bit, because what we need to do here now is we actually want to model the state of our objects through the type system. So the example that I want to start with is the simple two-phase initialization example that we mentioned earlier. So I have a widget here. I can just construct the widget, but when I construct it, it is not in a fully initialized state. I have to call the init function first, and only after it has been initialized, I can do stuff with it. So if you worked on a code base that uses types like this, you probably know what happens. People forget to call the init all the time. And then, yeah, you end up with calling do stuff out of contract. So one easy solution that you could do here is you just say, well, I just don't allow constructing a widget that is not initialized, right? So I wrap it away. It has to be initialized. And for some use cases for two-phase initialization, this makes sense, this works. But in other use cases, like the reason that you separated the two is that you actually need to separate the point of construction from the point of full initialization, right? So you can't just force the two always to be executed together, because that would defeat the point of having them as separate phases in the first place. So what can you do if you are in such a situation? And the way that the type system could help you here is you just split the two states into two different classes, right? So you have an uninitialized widget class, and that one gives you only the operations that are safe to execute in the uninitialized state. And then the do stuff function, the ones that requires previous initialization, that actually goes into a separate class. And that class is now not directly constructible, but you can only construct it from an uninitialized widget by performing the initialization. So what you will have is this initialized widget function here that consumes the uninitialized widget and returns you back the fully initialized widget where you can now do the interesting stuff. And so this is one of those patterns, I alluded to this earlier, where it would be really nice if we had a destructive move and the uninitialized widget would not keep lingering around after I pass it to this function. But I mean, like people will usually not get this wrong, right? Like once you moved it into the initialized function and then you keep using it afterwards, it's probably reasonably easy to spot. So you might have seen a similar pattern like this in other contexts, and it also has a name. It's called a functional update. Since like when you do mutation in functional programming languages, then you always have this pattern, right? Like you pass your data in, and since you cannot mutate it, it's like it goes into the function, and then the function returns you back the modified data. And if what you wanted to do was actually a mutating operation, then what you do is usually like you assign it back to the same thing that you passed in, and then if the compiler can figure out that, oh yeah, the thing that you passed in, I'm actually not going to is not going to be used anymore afterwards, then it might actually be smart enough to turn the whole thing into a mutating operation, right? So this is an optimization that functional languages can do to avoid having to copy stuff all the time. The difference that we have here is that we don't just get back a new object, we also get back a new object of a different type. But if you think about this, if the operation that I want to execute depends on the value of the thing, then this actually makes perfect sense, right? If the value changes and the operation does not make sense anymore on the value, then the type has to change, right? Then the operation also goes away with the change of the value. So I think this is a pattern that allows to model these kind of states very well, and I think it's actually underused. Like I think we don't do this enough because it can really help make the stuff more bulletproof against misuse. So let's look at other variants for this. So a slight variation of this is the execution token. So what I want to do here is, again, I want to restrict the circumstances under which a function can be executed. Only want to allow it in specific contexts. The problem with the example that we had before was in order to turn the uninitialized widget into the initialized widget, I basically had to move the whole state of the object into a newly constructed object. The execution tokens are a bit more lightweight here. So again, the execution token is something that construction of it is privileged, right? I can't just fabricate one out of thin air. I have to, for example, go to a provider that checks whether it's fine for me to get it, and then provide me with one. And then the function that I want to control access through the execution token needs to consume the token, right? That's the crucial part here, because if I can just make copies of the token or just like retain it for arbitrary amounts of time and pass it out, then again get these weird like spooky action effects where the token could get invalidated. And this is probably the cleanest way that we have in C++ to ensure that this does not happen. And again, like your mental model should be that the move destroys the object, right? It really consumes the token here. So one example where we could use something like this, again, a graphics API, this time the Vulkan API. So what Vulkan allows you to do is it allows you to record a whole number of actions that you want the CPU to execute in such a command buffer. So you make all kinds of calls, like I want to copy the image, I want to render some stuff, and all of this stuff gets recorded into a data structure on the CPU, and then you give this whole command buffer off to the API, and then it says, okay, now I'm going to do all of this stuff that you recorded in bulk on the GPU. This is very important for performance. The thing is here, like you have to follow a specific control flow here, right? You first have to say, now I want to begin recording of the command buffer, and then the state of the command buffer might change in between, right? Like if you need to begin a render pass before you can issue certain commands that are related to rendering and so on. And if you mess up the order, if you call any of these functions in the wrong context, then it doesn't work. So the Vulkan API is just, it's a C API, right? It's just 3 functions, so they don't do anything to protect you here. But again, you could try to encode these different states in the type system, right? You could say, yeah, I actually have like a command recorder class, and then the different commands that I want to record, they are member functions of this class, right? So if I don't have a recorder, then I cannot issue any commands, right? Because they are member functions, right? And then when I change the state, when I go to into a render pass, for example, I get a different object, right? And that then has all of the commands that are related to rendering and so on. And this is already better what we had before, but it still does not enforce this kind of structure, what we've seen before. So we can combine that with the functional transformation that we saw earlier, and even say, yeah, like what if actually if I start a render pass, that actually transforms the command recorder into a different type, right? That then has different capabilities. So in that case, like the restrictions that I have to the control flow here are represented by the types that I have available, right? So it is just impossible to call the command in an invalid context, because I just don't have the capabilities, right? I don't have the type available that I need to call the command if the context is not right. And like generalizing this to the extreme means like I can model arbitrary state machines like this, right? So if I have a state machine, then I have different classes that describe the different states and the different events. And the state transitions are then really transformations that turn like one of the states, like represented by one of these state classes, into a different state, which means into a different type, right? So we see it here, like the transition function, it consumes the state, and it returns me back a new state object. And the type system now makes it impossible to like accidentally be confused about what state I'm in, because it's all different types, right? And I cannot get it wrong, right? The type system enforces that I respect the constraints here. So there are, of course, trade-offs here, right? So on the one hand, I get this full control here. There's this awkward thing that the move semantics, they leave behind these dead state objects, right? With each transition. I will also now have a whole zoo of types, and unifying this again is is kind of difficult, right? I can try to use like type erasure to so that I can just store arbitrary states again, but then I again lose some of the restrictions that the interface imposed first. So it's a trade-off here, right? Like going full out like this. If you have a use case that is sufficiently static, then this might be a good fit. But not all use cases are like this, right? So it's like this is not a recommendation, change all your code to be completely static like this. It's more like consider patterns like this if you haven't done before. And if you actually do encounter a use case where it's a good fit, then consider doing this. Like to give a little bit of contrast here, there is a state pattern in the Gang of Four design patterns book. And this one approaches the problem from a different angle, from like a runtime object-oriented programming angle, where they just say, okay, like you have a state base class, and then your individual states in your state machine, they all derive from this same base class. And now what your context has is, so you have this do stuff function, which does different things depending on which state your state machine is in. And the Gang of Four pattern is now, the context holds on to some state, but you don't know which state, right? Because it's a polymorphic handle to it. And now if you want to set the state, what it does is it switches out this state object that the handle points to. But the do stuff function, there's no confusion there, right? It does not need to handle which state it's in because the virtual dispatch here does that for you, right? It ensures that you end up in the correct function. So this is a different way, which is like a more like object-oriented, more runtime-oriented way of doing the same thing. So in conclusion, hardening interfaces to make it difficult or impossible to violate preconditions is a good thing. You should, in my opinion, try to do this without widening the contract if possible, because usually widening the contract doesn't really get rid of the problems that you want to get rid of here. There's these two fundamental classes of preconditions. You either want to restrict which arguments can be passed to the functions or the context in which the functions can be called. And we saw a variety of techniques that allow you to do this. These were just examples, but hopefully they were somewhat inspiring for what you could do in your own code base. And yeah, there's always trade-offs here, right? Like restriction always also means you make it less flexible, maybe less usable. So yeah, keep this in mind when you do this. And that's my talk. Thank you.